Hello students. So in this video we are going to discuss about the concept of equilibrium. That's the first thing. Second, what is linear momentum, conservation of linear momentum, and what is impulse and impulse momentum theorem. Right. So these four topics we are going to cover in this video. Okay, so let's start. So what is equilibrium? Equilibrium. So equilibrium means the net force on the body, net force is going to be 0. In terms of vector, if you write, then it is a null vector. Okay, net force is 0. Right, so when the net forces are 0, right, so there can be a combination of forces acting. Let us say if there is net force 0 means no force is acting, that you can say. All forces are acting but they are balanced. For example, suppose if you take body and let's say there are two forces acting. So two forces must act in opposite direction. Let's say this is F1 and F2 vector. So for this system to be in equilibrium, it is having two forces, right? So for this, the sum F1 vector plus F2 vector, that is the net force, has to be 0. So F1 vector must be opposite of F2 vector, right? Equal and opposite. Similarly, if I take a body on which three forces are acting, so let's take this body. Here three forces are acting. Let's say F1, then F2, and then F3. Three forces are acting. Here we can also consider Lami's theorem. That also we'll discuss here. What is Lami's theorem? Lami's theorem. Suppose this angle is alpha, this angle is beta, and this angle is gamma. Okay. So first of all, the body is in equilibrium. Body is in equilibrium. And the three forces, these three forces are concurrent. That means it is passing through one point, and these three forces are coplanar. This have to be coplanar. Why? Because according to triangle rule or parallelogram rule, if you want to balance this, so sum of the two, let us say you want to add F1 and F2, sum of these two should act exactly opposite of the F3, right? This is the resultant of 1 and 2. So the resultant of 1 and 2 is produced in the plane of 1 and 2 only, right? And this R has to balance F3, so it should be in the same plane. So that's why these three forces are coplanar. Concurrent because it's passing through the same point. Okay, so if these conditions are there, then we can apply Lami's theorem. F1 by sine alpha, F2 by sine beta, right, is equal to F3 by sine gamma. So this rule is Lami's rule or Lami's theorem. This is also called sine rule in maths, right? Okay, but if there are four forces, then they may not be in the same plane. They may become different, planes, and still they can be in equilibrium. Okay, right? So this is the concept of equilibrium. Now let's extend this concept or some examples if you want to see. Let's see some examples. Equilibrium. So suppose if you consider, let us say there is a body which is being balanced. Okay, so a body is being balanced. This is a block, let us say. This block is being balanced, and how it is being balanced? This block is being pulled by some force. let's see like this, some force, and this is tension in mg. So it is in equilibrium, and they can ask you to find what is this angle theta. This theta is the angle made by the string with the vertical. So the shortest way to find out is, you should know that the resultant of these two must give a force, let us say R, and that R must be exactly opposite of the tension. So if this is theta, this definitely must be theta, right? So this head force is F, right? This is mg. So now directly you can say tan theta is equal to F by mg. Directly, in just one step you will calculate theta. Tan inverse of F by mg, right? Okay, so in this manner you will be able to calculate. But by resolution also we can do, right? Resolution, how do you do by resolution? This is the F, this is the mg, right, and this is the tension. So let us resolve here. Now here, because the body is in equilibrium, you can resolve any of the forces along any direction. You can resolve. Let's say here we are taking along x-axis and y-axis. So tension can be resolved. This side will be tension cos theta. This side will be tension sin theta. Okay, tension cos theta, sin theta. So tension sin theta will balance mg, and tension cos theta will balance F. So you can take the ratio, sin by cos ratio, tt ratio. So it will come, right? Tension sin theta is mg and tension cos theta, right? So divide, this is first, this is second. So tension sin theta by tension cos theta is equal to mg by F, right? So from here tan theta becomes mg by F. Correct? Tension cos theta is F, tension sin theta. Have we taken the angle correctly? No, I think here the angle theta we did not take properly, because this angle theta, when you are drawing here, this should be the angle theta, right? That's why this is not coming. So this angle is not theta. Theta is this angle. Okay. So I think the sin cos will interchange, right? This will be the angle theta. So this will be t cos theta. This will be t sin theta. Okay. So here we will interchange them, right? So this will also interchange, isn't it? So you can say that tension sin theta is balancing up, tension cos theta balances mg. Then you take sin by cos ratio, F by mg. So tan theta is F by mg. So properly if you draw the diagram, same result you can get. But this is a better approach now. By one step you can calculate. Okay. This is about equilibrium. So there will be variation of concepts involving equilibrium. Next, let us understand conservation of linear momentum. So if the net force is equal to 0, then the system or the body is in equilibrium. Okay, there can be a system also, which on system means then you have to add all the forces. That net force has to become 0, and remember this is the rate of change of linear momentum. Suppose you are taking a system. So we have to take rate of change of linear momentum 0. So from here you will understand momentum of the system will become constant, right? System momentum will become constant. Okay, there are many examples where this is considered, right? So suppose if, let us say there are two bodies which are interacting. This is one body, and let's say this is another body. Okay, and ground is also there, but this is a smooth surface. Now suppose you have applying a force F. So there is a normal force, right? Let's say this is the first body, this is the second body. Second, we'll apply some normal to the first. First, we'll also apply normal to the second. So if you take the total net force on the system, of course it is not balanced, right? But if you consider F1, F2, where you can balance it, let's say there is a force F1 you are applying and there is another force F2 is being applied and the system is balanced. So on the system, if it is balanced, then total momentum of the system will be constant. Okay. So of course net force on the system F1 plus F2 will also be 0. If you want net force on the system, you may write this as F1 with sign. If you write, right, let's write this with sign as a vector. So F1 is in positive direction and this normal is plus, this is minus normal, minus F2. This must become 0. So that's why you will see this force F1 and F2 will be equal. Now this is just a crude example. If you take another example of collision, collision of two bodies, collision of two bodies. So if you take collision example, let's say this body and this body, they are going to collide each other. Okay, so if the bodies are collide, let us say this is another body, they may not be exactly spherical, but when they collide, then there is some force acting on this and same force will be acting on this, right? So let's say this is like a normal force, contact force. This is the first body and this is the second body. So let us say they are moving before collision with velocity u1, u2. Its mass is m. So let's say m1 and m2. So after collision, they may separate out with some velocity, let's say v1, v2. Okay. So in such collisions, net force, if you take these plus and minus n will get cancelled because their action and reaction forces, they will cancel out each other. So the momentum of the system will be constant. Here system momentum is momentum both, right? So m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So this is called momentum conservation. Here v1, v2, u1, u2 are not the magnitude, right? It is just a factor. So with signs it will automatically come. Okay, or in general, if you want, you can put a factor here like this. Okay, you can put it. So this is called momentum conservation. Total momentum we conserve. So there are some examples here of also recoiling of a gun, recoiling of gun. So suppose that there is a gun, right, and this gun is firing, let us say. Okay, so some trigger is there, let us say, and this trigger is being pulled and some bullet is coming out. Okay, so this is a bullet, let us say, bullet is coming out like this with a velocity, let us say v1. This will recoil in this direction, v2. Mass of this bullet is small m, mass of the gun is capital M. Okay, so before firing the total momentum was 0 because system was at rest. After firing also total momentum must be 0. So initial momentum must be equal to final momentum. What is initial momentum? 0. Final momentum mv1 plus capital M v2. Remember, this is with this is without sign, it's a vector. Okay, so if I want to find v2 will be minus m by capital M into v1. Okay, minus sign shows that the velocities are opposite, right? So these are certain examples of these forces. Another thing is that there is a more better example of impulse momentum theorem. So what is impulse and impulse momentum theorem, we will understand. Impulse is nothing but force into time. Let's say delta t is the time interval. This is called impulse. Impulse, better you use the word J. J is a vector symbol for impulse. Okay, it's a vector quantity. Here we are assuming that force is constant. Force vector is constant. Okay, so force can be written as change of momentum by time, right? Change of momentum by time. So you see delta t will get cancelled. It will be impulse will be same as change of momentum. So the concept of impulse is nothing but force into time. It is change of momentum. In case force is variable, J can also be written as integration of f vector dt, right? Which will come same as delta p vector. So this is what is impulse momentum theorem, right? And sometime the graph of force versus time graph will be given, right? Let's say this is force versus time graph, and if the graph is given like this, so the area under the graph between two time interval or instances, this area, what does this area represent? Okay, this area under the graph will give us what? This will give us impulse. Okay, integration of f dt, that will give us impulse or change in moment. Okay, that is the area under this graph. Area under force time graph. Force time graph. Okay. So these applications will be coming in the problems that we'll see. So thank you for your attention.